might as well get started on it. Okay. So I think, and you can see my screen, right? Sure. The files that I'm going to explain about are available on my website, and you have to uncompress them, put the files into an uncompressed folder and all that. And then when you do, you'll see that in that folder you have these files. This is the one that we're running right now. This is the R script that I've got pulled open in RStudio over here. So that's what that is. So the first thing we want to do is we want to set the working directory, and we'll set it to the source file location. So it just sets it to wherever we have the script. So it'll set to that folder. Well, if these packages aren't already installed on your computer from some previous whatever, you'll need to install them. If they're already installed, you don't ever need to do it again. That's why I've got it hashed out, but you will at least need to load the libraries every time. This file here, and I'll double click on it, is the same one from the other tutorial. So this pairs up with the one about running a QTL analysis. This is afterwards. So this is the same file from there. No difference. Got all the genotype data for every locus. And you read across here, here's a particular strain, and here's all of its genotype data, where A means unmethylated and B means methylated, or the reverse, whatever it is. Doesn't have to be methylation data. This could be, for any QTL analysis, this could just be the allelic data, which genotype there is at that particular locus for that individual across all the loci. So there's nothing different there, but do note that the labels here, I mean, you can label things however you want, but you have to make the labels consistent across all the files. So here, the individual strains are called EpiReal1, EpiReal2, etc. And whatever they're called, it's got to be the same across all these files. So there's that one. And then if we look at, let's say, this file here, again, notice that they're called EpiReal1, EpiReal2, etc. They're not sorted in the same order, but this here is the raw data. This is from the Cortillo et al. Study, but it doesn't matter where it came from. This power analysis is for comparing the QTL results of 2 different phenotypes, not 3 different phenotypes, not 6, not 4. It's for comparing the QTL results from exactly 2 different phenotypes. And it's for 2 different phenotypes based upon the same genotype data. Yeah.
What flowering data is this? I know
This
we could teach code, but what exactly was it? The rosette or?
This is the actual Julian flower
Okay.
data. But again, this could be any phenotype. You just would want to make sure that, you know, probably you're going to want to be comparing the same the same phenotype, or yeah. So this script is set up for when you're redoing a QTL study that somebody else did using the same strains and probably the same phenotypes or very similar phenotypes. And you want to compare your results to theirs, and you want to see if why there's discrepancies between your results. Because if you'd think that if you're using the same strains and you're measuring the same phenotype, that you should get the same QTLs as the previous study. And so this script is to do a power analysis to see when you do find discrepancies between the two studies, what QTLs you find, what's going on there. Could it have something to do with statistical power? So we'll come back to this sheet here in a second. But next, I wanted to show you this file, QTL file pheno.csv. This also comes from the previous tutorial. But the important thing here is, for the previous tutorial, you could have had more than 2 phenotypes. You could have added in and had 10 phenotypes, however many you wanted. But for this tutorial, it has to be exactly 2. So I have it set up here where it's got your flowering time data compared to the Quartillo flowering time data for each one of the epirils. And this is the average flowering time. So this is the average flowering time across all of your biological replicates for that strain. And this is the average flowering time across all of the biological replicates from the Quartillo study for that strain.
Are those missing ones on mine? Are those the ones we had to discard from the second chamber? Or
the missing data? That's a great point. I see that in the Quartillo study, this was a super late flowering strain. Like 52 days is like way later than the others. It could have been that we just didn't wait long enough for it to flower before we ended the study.
that makes sense because all of the ones that are missing are up there.
Yeah, this one's also a really late flower. This one is somewhat late. So it's not always clear why some of them we didn't get flowering data, but for some reason they didn't flower for us. But notice that when we didn't have data, we left it blank. So for this script, when there's no data, leave it blank. So if you have data from one study for that strain, but not for the other, just make sure that it's, correctly coded like we have it here. But pay attention here to the names of the phenotypes. So this is what we're in this QTL file pheno. This is the name of your flowering time data, and then here's the name of the Quartillo flowering time data. Now, this is not the raw data, right? Remember, we just mentioned that these are the averages across all the biological replicates. For the power analysis script, we also need the raw data. So this file here and this file here are the same as in the previous tutorial. Although be careful again that this one should, if you had more than 2 phenotypes here, you got to winnow it down to 2 phenotypes. But otherwise, these 2 files are the same from the previous tutorial. This here is something new. So let's look at this one again here. The name of this file is Quartillo Julian flowering date, the .csv. So this is a comma separated value file. So it's that CSV spreadsheet format. The name here of the file before the file extension, this name is the same as the Quartillo phenotype here. So the phenotype column in this spreadsheet matches the name of this file. So make sure that if you're ever doing this with some other phenotypes, just make sure that the name of this file matches the name of that column in QTL pheno. Let's have a look at it here. This is the raw data from Quartillo. And again, if there's anything missing, just make sure that it's left blank. And you'll need to save this out in a CSV format. But the first, and it should have the exact headers that you see here. So the first column should say strain, lowercase. The second column should have that phenotype name again. but this is the raw data. So here, instead of having the averages for each strain of flowering date, we've got the actual flowering date of each biological replicate.
You only did 6 per strain.
Right. I think we did 5 per strain. So we were in the similar ballpark, I think. But, and again, be careful that your strain names are in the same exact format as your strain names in all the other files. So don't have it be called EpiReal 105 in one file and have it be called 105 without EpiReal in another file. Don't have EpiReal space 105 in a different file. It's got to be exact. Okay, so now we've got the raw data, and we've got, which is something new, which we didn't have in the other script. But we also have the averages, which is, again, carried over from the previous script. And we have this raw data for each of the phenotypes. So here's the raw data for your phenotypes from your experiment. And here we see again that, again, remember the name of the file, it's this .csv, but this part here matches exactly the name of that phenotype column in the qtl _pheno.csv file. And this is how you set up the data sheet. That phenotype column should have the name of the phenotype again. Capitalization matters. Make sure that if there's, like there's a capital J in here, make sure that there's a capital J throughout all of the places where you have that phenotype name, whether it's the file name or whether it's one of these columns, whatever. This file here, stats.csv, also comes from the previous tutorial. So you'd want to run that. I mean, this is obvious, we've already done it. But if you were doing this again in the future, you would want to run that first script first, which generates this file stats.csv. So that's where this came from. This was from the previous tutorial. And this has all of the significant QTLs. So for instance, on chromosome 1 at position 26.7, there was a significant QTL in your data. That's the peak of the significant QTL. Of course, it's an interval, but that's the peak. That's the most significant marker within that interval. And then we have all this other data about that marker. So this will also be important for the power analysis, but that's where this came from. We generated that with the previous script. So the only things new here are this data file, which you have to just already have, and this data file, which again, you'll have because you collected that raw data. All right, we've already loaded in these libraries. So next we're going to import in the genotype data. So we're going to import in this file here, which has all of that. Sometimes it's called the map file. So we're going to go ahead and import that in by running lines 16 and 17. All right. And now we're going to run it. We're going to read in that stats file that we were just talking about. Make sure you have all these files in that same folder along with the R script. All right. And then it's not really, this step's not important. It's just part of the script. So you run this. Now we're actually going to perform the QTL analysis again. We already did it for the first script. Here, we're not going to be generating those plots with the peaks and the intervals, but as a part of doing the power analysis, we actually need to run the QTL analysis again. So we're going to actually run it here on these lines. And I have it set up with the same number of permutations as in the previous script. Okay, so that part's done. Now we're going to skip ahead to line 37. So again, this is about the raw data. So here, first we're going to look at the phenotype data based upon the averages. So we're just going to look at it on our screen. So, well, we're going to look at the names of those phenotypes. So we have that phenotype and we have that phenotype. And so that means that for our raw data, again, this is what the name of one of those spreadsheet files has to be. And for our other raw data, this is what the other name has to be, except with a .csv at the end. So we have those files here. We're going to read those both in. And you need to read them in the same order that they occur in this file. So do you see how the first phenotype in that QTL file is Raoul Julian flowering date? So that means that when we read in the raw data, the first raw data file that we read in has to be Raoul Julian flowering date. They have to be, you have to read in that raw data in the same order. So that's why this raw data file is first and this raw data file is second, because it's the same order as they occur here in this phenotype file that was used for the QTL analysis. All right, so we're going to go and read in those two traits. Okay, that's trait 1 and trait 2. That's the raw data. We have to do some cleanup steps here. And that'll be lines 54 through 65. Now we're ready to do our first power analysis. You do the power analysis for specific markers. So you'll always need to change the script depending upon the particular power analysis you're doing at that moment. There's never just one power analysis you do for all the data. You have to look at your results and decide where you see some discrepancy and you want to check the power that you had to detect an effect at that marker. You always have to, it's always going to be the human element there. So, oh, wait. Okay, before we actually have to, the human element gets involved, we need to do some other steps here. We have to calculate something called heritability, which I know that you know about from the evolutionary genetics class, but I won't say a lot about it here, but we have to calculate that for the first phenotype and then for the second phenotype. Part of our power analysis. Which goes to prove that heritability is actually something that one uses, because we're actually using it here. Okay. Now let's look at that stats file. And this is where that human element comes in. So let's just as an example, let's look at this row 5 here. So we can see that there is a significant QTL on chromosome 2 at position anyway, biggest peak within that interval is at position 5.3. And we see that it's a QTL that is in your data. And also we see that there's no other QTLs on chromosome 2. So forget about the rosette leaf number data here, because we didn't include rosette leaf number in this, because remember, here we've got 3 traits. Here we've got rosette leaf number from your data, we've got flowering date from your data, and we've got flowering date from Cortillo's data. But we can only have 2 phenotypes for this power analysis here. So forget about rosette leaf number for now. So that's why I just started looking here. There's no other QTL. There's no Corteo doesn't have a significant QTL on chromosome 2. If you look at the Corteo significant QTLs, she had one on chromosome 1 and one on chromosome 5. Whereas you had QTLs on chromosomes 1, 2, and 4. So the first discrepancy that we're going to look at here is, why is it that you had a significant QTL on chromosome 2 and she did not? Okay. And we'll talk more about that when we look at the results. But that's why I picked row 5. So we're going to focus on that particular marker, on that particular QTL interval that contains that marker. And we're going to look at that. We're going to look at the power to detect the effect. We're going to look and see how much power Corteo had to detect that effect. Because if she didn't have a lot of power, statistical power to detect that effect, that would go a long way towards explaining why she didn't find it. So this step here, on line 116 of the script, you're going to change that every time, depending upon which marker you want to focus on. So we're focusing on that marker on row 5. So we're going to run this line of code here. If you wanted to focus on a different marker, then you would set that row to a different row. And again, that row, that means when we're looking at that stats file, these are the row numbers here. So this is why I'm referring to row 5 right here. Okay, so we've got that line of code. Now we should just be able to, this is always dangerous, run the entire script and get all the output. So after all that explanation, once you have all the files, if you just change a few things in the script, you should just be able to run the whole thing and do the power analysis, and then we can discuss the results. So that's lines 118 through 269. And it looks like it ran just fine. So I'm going to go ahead and open that up. Hold on. Okay, so we're going to go through these 3 files, which were generated by the script. So it all ran. First, we're going to go through this one called marker compare blah, blah, blah.csv. So this is, again, based upon the QTL that you found on chromosome 2 at position 5.3 on that chromosome, that being the highest peak. So that's how the file is named. And it's .csv. There's also .pdf. We'll talk about that one later. But for now, we're going to look at marker compare blah, blah.csv. Double click on that. Just going to stretch open these columns so we can see them better. So we're doing a comparison here of your phenotype data to the Corteo phenotype data. This is only for that particular QTL. So the first thing to show you is the power. Yeah. And this is the this is based upon the conventions of Cohen for doing power analyses, where anything above 0.8 is considered sufficient power to detect the effect of interest. So, not surprisingly, the power that you had to detect the effect was 0.99. I need to explain this a little bit further, because the way I have it set up is a little bit weird. What the script does is we use your, oh, there's one other thing I need to show you about that script, actually. So we went and ran all of this, but I do need to actually go back and tell you something. Every time you run the script, you're going to want to change this here, this line 138. So we have two phenotypes, yours and Cortillo. And if we look at the order that they occur in the QTL phenotype file and the order that we read in the traits, we read in yours first and the Cortillo data second. That's important. So yours is first, hers is second. So let's go back down to line 138. Right now, we're comparing your data to hers at that one site. You have the QTL, she doesn't. So this line here is to tell the R script whose data is the phantom data. And by phantom, I made this up. You have the QTL, she didn't. So she has, in my analogy, she has a phantom QTL there. It doesn't exist, like a poltergeist in the room or something. So you need to tell R which of the two phenotypes is the one with the missing the QTL, with the phantom. You could also think of it like a phantom limb, like if somebody has had some sort of a traumatic amputation and then they still think that the arm is there. So that's the sort of the metaphor that I was going for. Now, if you were doing a power analysis where Cortillo had the QTL and you didn't, then the phantom population would be 1. I mean, phantom phenotype would be 1. So that's what that means. And that's why we said 2 here, because we said, your phenotype data is the first column. You had it, the QTL. Her phenotype data was the second column. That's why it's a 2. Hers is the one with the phantom data where the QTL is missing. So be careful about that when you run it. Now, this is something here called effect size, which you and I can follow up about more later. But the effect size has to do with how different the flowering times are between the individuals that have one allele and the individuals that have the other allele. Another way to think about effect, and effect size is just kind of a more general statistical term. Imagine if you did an experiment with watering. Let's say that you gave one group of plants 10 milliliters of water a day, and you gave the other group of plants 20 milliliters of water a day. Let's say that the plants that got more water grow on average to 40 feet. And the ones that you gave less water to grow to an average of, like 6 inches. That's a huge difference in the height between the two treatments. That would be a huge effect size. On the other hand, you could have a situation where the ones that got more water, they grow to an average height of 7.1 inches tall. And the ones that got less water grow to an average height of 7.0 inches tall. So, and maybe there's still a significant effect there, maybe not, but the effect size would be a lot smaller. So it's still, the watering makes the plants grow taller, but there's less of an effect size. So that's just to give you the general idea of what that means in statistical terms, but it could be for anything. In your case here, the effect size refers to all the plants. Remember, you're comparing the two averages. Comparing all the plants that are methylated or whatever, that have the first one allele at that locus, to all the plants that have the other allele at that locus. And so think about that as like low water versus high water if you want, but there's some difference between the two groups. In this case, it's what allele they have at that locus. And then we're looking at their flowering times, this group and that group. If it's a huge difference in the flowering time between the two groups, that's a big effect size. If it's a small difference in flowering time between the two groups, that's a small effect size. Effect size influences your statistical power, which makes sense. If the effect is small of, let's say, watering the plants, it's going to be harder to detect that effect because random fluctuations in the results or in your measurement or something can wash out that effect. You may not see it. Like, let's say that, there wasn't perfect precision in how you measured the heights. Let's say that there was microenvironmental effects throughout the growth chamber where the plants that were growing over here had a little bit better conditions than the ones over there. Not things that were on purpose, but just it's never going to be homogeneous. All of those things can, if you just have a small effect size, can wipe out that effect in the results where you just wouldn't see it. You just wouldn't have the statistical power to pick it up. Whereas if the effect size is huge, even if there's little microenvironmental effects, even if you're not perfect in the way that you measure the heights with the ruler, I mean, if the difference is going to be 40 feet versus 6 inches, it doesn't matter how imprecise you are with the ruler, like you're going to see that effect. It's going to be huge. It's going to come up as statistically significant. So effect size influences power. Higher effect size, the more power you're going to have, all else being equal, to detect an effect. So the way that I have this set up is the script asks, okay, Cortillo didn't have the effect, but let's imagine that we take Cortillo's data set where, this is how many replicates she had. This is the heritability of the traits that she found. Just imagine her exact population, her exact study. If she had an effect, so here's the effect size in your study. You had whatever it is, 1.75. It's standardized effect size, but look at the effect size in her study. Like, you can see that your effect size is much larger than the effect size that she had for this particular. And what I did is I looked within the QTL interval for the marker in the QTL interval in her study that had the biggest effect size. So just did like the best case scenario. Like, here's the QTL interval where you found your significant QTL. Let's look at that within that same interval in her study. Where was there the biggest effect size? So we found so for her, it was this marker had the biggest effect size. Best case scenario. Okay, what was that effect size? It was much smaller. Now, so this power here is, what if in her study, what if in her study, she actually had this effect size? So what if she had your effect size in her study? What would the power have been? So that's what this means here. This means that in the phantom population, if the effect would have been this big, the power would have been this. So if she would have had an effect, if she would have detected an effect that was as large as the effect that you detected, she would have had the power. Probably would have been a significant QTL. But the effect size that she actually had was this. So this power here So really, when you're reading these results, the power analysis is really giving you the power for the phantom population. In this case, this is the actual power that was in that phantom population. And this is what the power would have been if the effect size would have been as big as the effect size was in your study.
I have a question.
Yes.
It might be a little bit out there. So obviously her effect size was not big enough and it tells us that her power, she didn't have the power. Apart from just looking at the power, is there like a threshold for the effect size that tells us, oh, this effect size is meaningless or this effect size is actually not meaningless, other than just by looking at the power, saying, oh, you know, she didn't have enough power to actually detect it?
That's a great question. The power is based upon more than just the effect size. It's also based on, we can look at the R code for this. It's based upon the effect size. It's based upon the genetic variance and the environmental variance. It's based upon the, so your question about threshold, there is threshold that plays in here, but it's the permutation threshold of the QTL analysis, you know, that dotted line that goes across. So there is a threshold, yes. So there is a threshold involved, but it's not. So your question was, is there a simple effect size threshold? There's not. You have to throw all of these ingredients into the soup to get power. You have to throw in threshold, genetic variance, environmental variance, number of replicates. Effect size is just one of those ingredients. If there was a huge effect size, but your study was crappily designed so that you only had 2 replicates per strain, that's still gonna bring down your power. So I'm just pointing out effect size here as one of the things, but and some of them I don't even have on here. Like I don't have on this spreadsheet environmental variance and genetic variance. I do have heritability on here. So this is so this column here is which marker. So this defines our QTL interval. And you can look up that QTL interval in the stats.csv file. But within that QTL interval, which was the most significant marker? And for the Cortillo study, this was the most not significant marker. Yeah, which had the highest peak in the QTL graph within that interval. And for Cortillo, it was this marker, which is at a little bit different position, but it's still within that QTL interval. This is the sample size. And by sample size, this refers to the number of different strains. So this isn't the total size of the experiment. This isn't based on the raw data. This column here is based upon for each strain, there's like an average flowering time. So in the Cortillo study, there was 123 different strains. And in our study, there was only 120 because there were some strains that we had. There's some strains that she was able to get flowering time data on that we didn't. So remember those blanks that we saw. Right. Those means we had our N, our number of different strains ended up being lower than Cortillo for that reason. Looks like we had 3 strains where she got data and we didn't. But this is based upon our data. This is based upon her data, this N. Number of replicates. On average, we had about 5 replicates, as we discussed, per strain. She had about 6. This is the heritability of that particular marker. So this is the heritability of your flowering time phenotype at your marker, the marker that had the highest peak. The heritability was 0.16. This is the effect size. Also, this is all your data. This was the effect size, 1.75. So same thing down here. This is all for the Quartillo data. This was the heritability calculated for this marker for her flowering time data using her population. This is what her heritability was. Her heritability was 0.447. So actually, she had higher heritability. So all things being equal, she should have had more power. But effect size was so much lower that it really dragged down her power. But so again, these effect sizes are based, this is all based upon your data. This effect size is all based upon her data, based upon the best case scenario marker within that within that QTL interval. Percent variance explained. We can talk more about that in the future, but this usually tracks with effect size, although not always apparently, because in Quartillo's case, even though she had a bigger effect size, her best case marker didn't explain as much of the variance as our best case marker. That not important to understand that detail right now, but this is all based upon her data, her marker, etc. And these thresholds, this threshold is based upon your data. This is the threshold from the QTL analysis from the previous video, in the previous script. This is that significance threshold from those QTL plots. This is for her data. This was the significance threshold for the QTL plots for her data. It's pretty similar. This is also based on her data. This is the load score, likelihood of disequilibrium score. And you can see that for the best case marker, the load score was below the threshold. In your case, for the best case marker, your load score was above the threshold. That's why it was significant. You know, if we look at that plot from the previous tutorial, and you'd see that that peak went over the dotted line. And that this is just another way of showing that this peak here did not go above this dotted line. So far, everything in this row is based upon your study. Everything in this row is based upon her study. The only difference is for calculating power. For calculating power, in this row here, this power, it's all wanting to calculate power for the phantom population. This power here is what if everything else was like the Quartillo study, but she had your effect size. This is what the power would have been. This is what if everything was like the Quartillo study and also had the Quartillo study effect size. This is what the power would have been. So here's what we can conclude. She did not have the power to detect an effect within that QTL interval. And the reason that she did not appears to be because of the effect size. If she would have had an effect as great as the effect that you saw in that QTL interval, then she would have had plenty of power to detect that effect. So we can say that, so getting back to our original question, why is it that you found a QTL in that interval and she did not? And it's a power problem because she didn't have the power. And the reason that she didn't have the power appears to be because of effect size, because the effect size was just so much lower. That's what we can conclude by looking at this. So it's not that, I mean, and there could have been other reasons for her not having the power. So for instance, imagine if these two effect sizes were the same, or similar, something like that. But let's say that you had 120, your N was 120, and let's say that her N was 4. Well, then if she had low power, I would suspect that the reason, I'd say, well, it can't be because of the effect size, because the effect sizes were the same. It can't be because of heritability, because she actually had more heritability than we did. But look at that. It's got to be because of the effect size. So we can, by looking at these results, we can first see, I'll just put this back to what the real data showed. If there was a difference in power, and yes, there was. And then we can kind of look at in the spreadsheet in more detail and surmise why was there less power. And in this case, it's not because Cortillo had a poorly designed study compared to ours. You know, it's not like she just barely used any plants or something like that. It just appears to be that when she did the study, that effect size between the two different alleles was a lot less. Why is that? That just happens when you redo an experiment. Could be, you know, the conditions, her field conditions may, because her flowering time data is from a greenhouse. Ours is from a growth chamber. Maybe there was something about those plants growing in that greenhouse that with that particular allele, there's some interaction between that allele and the environment that, you know, really dampened the effect size. Who knows? But this is something that you see happen across different experiments. So even though her experiment was just as well designed as ours, I mean, probably her experiment was a little bit better. She had slightly more replicates. She had slightly higher N. She had slightly more biological replicates per strain. She actually found higher heritability for the phenotype than we did. So she had a lot going for her. In spite of all that, she had low power. And the telltale reason for that we can see comparing all the metrics is there was just for whatever reason, there was a much lower effect size than the effect size that we found. Okay, so we've looked at that one particular output. We're almost done. But now let's look at marker effects. So here's the effect sizes. Well, actually, let's look at marker compare blah blah.pdf. Here is the effect sizes plotted out. So in your study, you know, within that QTL interval, the marker with the highest load score, you know, the highest peak on that graph was MM171. And so if you take all of the individuals at MM171 that had one allele, I don't know if it was methylated or whatever, versus unmethylated. So here's the average flowering time of individuals that had the one allele at that site. And remember, we only have to worry about two alleles because with Arabidopsis, everything's homozygous. And then here is the standard error around that estimate. So this is the average flowering time of all the individuals with that allele. And this is the standard error around that estimate. And then here's the flowering time of all the individuals with the other allele and the standard error around that estimate. So there's the effect of that allele on flowering time. I mean, it's all correlative, but so you have to be a little careful with the word effect. It's a little bit of a loaded word. But that's what we see in the data. And that's for this is for your marker, using your data, using your effect size, etc. Here's Cortillo within that same QTL interval. For her, the marker that had the highest load score within that QTL interval was MM378. This is all her data, her effect size, her everything. Again, here's that same alleles, AA versus BB. And here's the average effect size for her. So here's the average flowering time of individuals with AA. Here's the average flowering time of individuals with BB. Here's your standard errors. Notice that flowering time is not well estimated. Look at how big these standard errors are relative to the slope. So, in your case, we found that clearly individuals with BB flower later than individuals with AA on average. These estimates are well outside the standard errors. But with Corteo, her standard errors are overlapping. So if anything, her data shows that individuals with BB flower earlier than individuals with AA, which is the opposite of what you found. But her estimates of flowering date for AA versus BB were poorly estimated because you've got huge standard errors that actually overlap. So we don't actually know. I mean, our best estimate of the effect is that that flowering time decreases when you go from AA to BB, but it's poorly estimated. So that's just more information we can get from looking at these graphs, in terms of doing the power analysis. This is generated automatically. And so that data we just looked at is here. Here's the raw data. I mean, not raw data. Here, this data here, this number, you might look at this graph and be like, well, what is this exact number here? What is the exact standard error here? Those numbers are stored in this file here, markereffects.csv. So if we look here, we see for your data, which was MM171AA, we see what the average flowering time was for individuals that had AA versus BB. And then we see for Corteo, for MM378 AA versus BB, we see what the average flowering times were. And then here's your standard errors for each of those estimates. These are the plus or minus that go around those estimates for each one. So this is just to show you that you've got the actual numerical data there that was plugged in to make those graphs. In case in the future we ever wanted to go back and make those graphs prettier, start with the raw data from scratch and just plot them ourselves, something like that. Although we could also just clean up the graphs that were made by R using Inkscape or something. But this is just to show you that the actual numerical data is also given to you as output. There you have it. I think that's everything you need. So the next time you run this power analysis, you'll just pick a different row. And then all of these results will just populate automatically. Let me turn off the recording.